Media architecture refers to integrating digital media technology within architectural design. This type of architecture employs large screens, LED lighting, and projection technology to display visual arts, advertisements, dynamic lighting effects, and interactive elements. It aims to enhance the interactivity and appeal of urban spaces, often utilized in public areas, plazas, building facades, and art installations. Overall, media architecture transforms the appearance and function of buildings and enhances the technical and interactive qualities of urban environments, enriching the experience of urban spaces.
The Vega Sphere, also known as the MSG Sphere at the Venetian, is a compelling case study in LED-based media architecture. This architectural wonder, a Madison Square Garden entertainment creation in Las Vegas, is a massive spherical structure adorned with millions of LEDs. It is a high-resolution screen, showcasing dynamic images and videos and creating versatile visual effects. The MSG Sphere is a testament to the fusion of cutting-edge digital technology with architectural design and a striking landmark in the cityscape, revolutionizing the way audiences experience content.
Have you ever wondered about the intricate relationship between LED-based media architectures and natural light? How do these architectures manage color fidelity under natural light in different times and environments? The influence of natural light on the color rendition of LED displays, especially in outdoor settings, is a novel and crucial area of research. The fluctuating intensity and angle of daylight throughout the day can significantly influence the visibility of LED screens, underscoring the importance of this topic.
We conducted a rigorous study to investigate the impact of natural light on LED colors. We examined the effect of natural light at 3 different times of the day on the 12 colors of the Macbeth color checker, a widely used color calibration tool. Our choice of the Macbeth color checker, produced by X-Rite, was based on its precise formulation and global usage in color calibration for LEDs and digital cameras. This methodology ensured the reliability and validity of our findings. While the color checker typically includes 24 different color patches, we focused on red, blue, and green, their combinations, and neutral grayscales for this study.
First, we measured the SPD, spectral power distribution values of natural light at 3 different times during the day and noticed significant variations in radiation intensity. Comparing the absolute radiation intensity values made it hard to confirm if the waveforms were correct. So, we analyzed the radiation value of each wavelength in the SPD divided by the maximum radiation value to check if our natural light's waveform was accurate. Our comparison showed that the waveforms at 10 a.m. and 1 p.m. were very similar. Still, the red light component at 4 p.m. was relatively weaker, aligning with the natural daylight changes throughout the day. This confirms that our SPD measurements for the 3 different times are valid.
After laboratory instrument measurements, we obtained valid SPDs for 3 different times of natural light, along with the reflectance factors for our selected 12 colors under the D65 lighting standard. Using the CIE 2 de Grolin Standard Observer, CMF, we determined the objective colors of these 12 colors under the 3 different light spectra. The distribution of the 12 selected colors under the 3 natural light conditions generally matched their original positions, but there were some slight differences. To understand the extent of these differences, we used the objective color under D65 as a reference to study the delta E values. We created comparison charts connecting the 12 colors under the 3 time periods and the D65 reference lighting. These charts show that the color differences are quite significant under natural light at 4 p.m.
By doing research, we found that as the sun moves closer to the horizon, the path of sunlight through the atmosphere becomes longer. This means the light has to travel through more of the atmosphere, which increases the scattering and refraction of the light. As a result, the blue wavelengths of light are scattered more, while the red, orange, and yellow wavelengths can travel further.
After doing the calculations, we found that the delta E values were all under 10 under the 3 types of natural light. The slightest difference was at 10 a.m. with the neutral 5.5 color, showing a delta E of 0.08, while the largest was at 4 p.m. with the green color at 7.66. This shows that throughout the day, as the natural light changes, people perceive differences in the same color displayed by media architecture. To minimize these variations, we need to adjust the light emitted by the LEDs in the media architecture itself.
In practical terms, there are already some research directions for LEDs to reduce color differences at different times of the day, such as brightness adjustment, color calibration, color temperature adaptation, etc. First, consider the brightness adjustment of LED screens, which measure brightness in nits, with outdoor screens typically ranging from 4,000 to 8,000. These screens can adjust brightness manually or automatically based on the surrounding light conditions. For instance, just like our phones, they increase brightness during the day to counteract sunlight and decrease it at night to reduce glare.
There are more examples like color calibration. LED screens undergo color calibration to ensure the colors displayed are accurate and consistent. This involves adjusting color temperature, white balance, and gamma settings to match recognized color standards such as sRGB or REC.
Finally, the color temperature adaptation. The screen's color temperature can be adapted to match the changing light conditions throughout the day. For example, cooler color temperatures are used during the day to complement the natural daylight, while warmer tones are preferred at night for a more relaxed viewing experience.
In conclusion, media architecture is gradually becoming more imaginative. Usually, we use the CMF method to calculate delta E straightforwardly. However, we need to reverse this equation to figure out how to adjust LEDs to minimize the impact of natural light. We're excited to see new calculation methods and technologies elevate the beauty of cities through media architecture to a whole new level.